N plus, but there are more free electrons in the N plus, to the point where the N plus is basically like a free wire compared to the P type, where the P type will block electricity going through it more than the N type would. Okay? So the current goes into the N type substrate, the N plus, from the source, and it can't get to the drain, right? Because there's this P type substrate in the way. It's awful. Why? What the hell? You can't get it through. But that's where the gate comes in. So you'll see the gate also has a signal on it. That's because we'll take our input, we'll take the input signal that we like, and we'll put it to the gate so that we can actually take electrons from the P-type substrate and attract them to this top between the two N-type substrates. So think of this as like a literal pool of like magnetic metal, right? And you turn a magnet on, and what's going to happen? All of the metal is going to go onto the magnet, right? That's the same thing that happens with the charges and the free electrons. So you apply a positive charge to the gate, free electrons will go up towards the gate. And if you apply more positive charge to the gate, you get more free electrons up towards the gate. When you have even more and more of these free electrons, it allows current to actually pass from N plus at source to N plus at drain. So what that means is that you'll actually have the ability to transfer the electrons from here to here through this P-type substrate, because all the free electrons in the P-type substrate will go up between the two ends, and you'll be able to connect the circuit essentially. Very simple, and this is made with usually silicon now. It used to be made out of metal, and it's relatively simple. It used to be made out of aluminum because that's what they had. And the more voltage you apply to the gate, the more current you're able to let through. What this means for us in audio is that the source can be a super high-powered current that you'd like to output. So let's say your amplifier wants to be louder than the source, right? We want it to be super loud. So we take, so I shouldn't have used source. We want the input wave to be amplified to a larger amplitude than we have. Great. We take a power supply and run its current through the source of this MOSFET. Then we take our input, which is our music file, and we apply it to the gate. The gate then attracts at crazy fast speed varying amounts of electrons to go between those two ends, okay? And then we're able to pass different currents through the ends, or through the P, to the other end and out the other side, which will then eventually go into your headphones, right? So what this means is that using this, we can have two signals that never touch, but one influences the other. To me, that was like, mind blown.
Really cool.
Yeah. So this is super common. You can also use a tube to do this. Tubes will apply second harmonic distortion and other types of distortion in a way that some people like. If you don't know what a tube is, it's literally a vacuum tube with two plates on it and a gate between it that controls how much the electricity can flow through them. It's very much the same thing, but using a different technology. It used to be used before this was developed, but this is significantly better as far as like making it go more accurately. Does anybody have any questions about how this works? Because it's very important for our next step where we're going to talk about amplifier classes. Cool? Cool. There's more info at the link if you want to see if we can.
Good to mention that this is like why computing exists.
Oh, this is a transistor, and this is literally why this exists. And you can put 5 billion of these on a chip, maybe more.
To be fair, this one's really cool because it allows high voltage.
Yes, that's what makes this one important for us. It allows we can pass a very high voltage through this, and presumably we can use multiple of them.
You can pass high voltages through small ones too, but it's the crap out of
Yeah. So, yeah. Okay.
So
Anyway.
would there be like different kinds of transistors specifically for audio purposes?
Yes, and they developed them specifically to be able to work in this paradigm, such that when they heat up, we want them to be less susceptible to temperature change, like we looked at earlier with the resistors. Same thing happens, except with the resistance inside of this. So that means that it's not actually able to amplify the current at the same points. And that's actually a good thing you brought that up, because this happens naturally as well. These will be non-linear, and that's how you get problems with your amplifier. Okay, so what this means is that it doesn't have the ability to pass frequencies, specific frequencies or specific, in this case, I guess it would be the gate being higher or lower, right? So if we have a higher charge at the top of the gate versus a lower charge, it might not be linear in its transition from, let's say, 0 to maximum. It may not actually travel at the rate that we want it to between those two. It may jump around with how much it allows as we transition from 0 to maximum. And it will say, like, you know, until we get to 1, I'm gonna be kind of tight, you know, I'm not gonna really let anything through. And then as soon as we get over 1, it might let more through than it should. And that kind of thing is how you get really bad amplifiers that apply distortion to your waveform. We're gonna look at distortion next.
And also, like with that, it's good to mention that most MOSFETs don't have like that. Most MOSFETs are designed to be nonlinear, so that once you get to a certain threshold, then it lets everything through.
Right.
It's not meant to be linear.
Right, and we want ones that are linear, so they're actually very different from ones you'll see in other applications. Great. All right. Now we're going to talk about amplification. This is definitely we've got past all the hard stuff. Now we're going to cover a bunch of cool stuff, and we'll finish up and we can listen to some audio. We're going to talk about amplifier classes. Most of them are super simple. We don't care about them. And now that we know how a MOSFET works and how pulse width modulation works, it'll be a breeze. So amplification, we have the red wave and we want the blue wave. We want it to be as perfect as possible when we do it. So we talked about harmonics earlier. Now that we kind of know how the current is going to be passed through the MOSFET, before we go looking at how it's set up, we're going to look at just what can happen to the waveform because of those non-linearities in the MOSFETs that are pretty much always going to be there. Even if you have really, really good ones, it can produce this, but to some extent you're going to see this. And you'll see the sine wave at the top has second harmonic distortion. So I'm actually going to have to probably flip back to the other one just to show you what we're looking for here. So picture our wave, for those of us who are here. Picture our wave looks like this. And now we have a second harmonic distortion is going to be a wave that looks like this, and it's like everything's fine, except that then it goes up here, and then it goes down, and then it goes back to match again. And you'll see this wave here is going to influence this value. And if you look, for those of you who are online, the wave that's going to be a problem is going to be twice the speed, because it's going to be the second harmonic of the original desired output. So we end up with, see how this trough is like really curved instead of pointy? So the tops are kind of nice, and the trough at the bottom is really curved. That's because what's happening is this wave is getting applied in a smaller amount to the original intended wave, and it's actually bringing this trough to be higher than it should be. So what that means is that as you have this second wave being applied to the first wave, because the MOSFETs and because the electronics will apply these things naturally because of how they're not linear, because they'll change based off of what they're allowed to, what they're able to put out for their output, and because sometimes electronics are just not perfect and electricity does really weird things with the period of the wave, it will apply these things, and you're going to have a waveform that is 2 times, in this case 2 times, and at the bottom it's going to be 3 times. The frequency of the desired wave is applied to the first one. This is what the waveform looks like, where you can see that the bottom is like not going all the way down to the place that it should. And the tops are also changed a little bit, but you don't have anything to reference them to. But you can see that this is clearly different. When you get to the third harmonic, you can see that it's actually affecting both of them, because it's going to be here. For those of you who can see my cursor, here, there's going to be one. And then there's going to be one in the middle, and then there's going to be one here, right? And they're going to be slightly off because it's 1/3 the frequency. So what that means is that it's going to actually, because you can see here's how powerful they are. So this is like the wave we want. This is its power. This is the power of the wave we don't want. It's been introduced into the system. It's the same thing here. So it's a smaller amount of power, and this is a logarithmic scale. So this is a lot less power. But either way, it's still influencing our wave to the point where you can hear it. This happens. This is why you have low quality audio. This is the problem with poor amplifiers and poor DACs. This is what happens. They introduce this because they're not made of parts high quality enough to stop this from happening.
Was it in the PWM wave? How to get back to an analog?
Okay, let's talk about that. This is a low pass filter. We're gonna get this at the end just because I tacked it on, but that's fine. This is a capacitor and a resistor. The voltage in hits the capacitor, but because it actually can't be let through at certain frequencies as much, it will end up being pushed out this way. That's my ELI 5 way of explaining this. That's the entirety of my understanding of this, is that specific frequencies, usually those of very high frequency, will be attenuated more, and low frequency will be attenuated less, and will be allowed to pass through the capacitor. And the others will go through the out. And what happens is that you take your pulse width modulated wave that looks like that looks like this, and when it spits out the waveform, it curves it exactly like you want it to. This is a really bad drawing, but it curves it exactly like you want it to by attenuating the wave as it goes, and it just like perfectly smooths it like you would want it to. The higher quality your parts here, the better it's going to smooth the wave. That's a whole other thing, and it can apply other types of distortions we are not going to talk about because they're way worse. But that's how we take the pulse width modulation wave that we got as the output from our earlier discussion about the integrals of the math, and we take that output and we run it through this filter. This is a simple one. There are way more complicated ones you can get. This is just the one that I figured was easiest to understand, and you end up outputting your nice sine wave that is literally just taking this square wave and putting it in to this filter, and you get this